Okay guys, welcome back to another video. Today we will take a look at strong induction, which is similar to the second principle of mathematical induction. So take a look at the strong induction. We let Pn be the statement for any integer n, and a is an integer. If we can show that P of a is true, and if you can show that if PA plus 1, PA plus 2, all the way to PA plus M, and then PM is true, then Pn is going to be true for any integer n such that n is greater than or equal to a. Alright, so let's prove this theorem, strong induction. So let's prove this. How come can we do with this proof? Again, we let Pn be a statement for any integer n, okay, such that n greater than or equal to a, where a is an integer. And then we assume that the first statement and the second statement are both true. So we assume that 1 and 2 are both true. Okay. Now what can we do? We know that n is greater than or equal to a. What do we have? When n is greater than or equal to a, we're gonna have that n can be a plus 1, a plus 2, a plus 3, a plus 4, and all the way and so on. Alright? And then we could use another variable because I want to start from another statement with 1. Okay? Instead starting from a, I start from 1. So we let L to be n minus a plus 1. Then what do we have? What happened? Try to plug in this a to n. L turns out to be 1. Okay. Next L will be 2 when n is a plus 1. So L will be 2. And then we're gonna have L3, L4, and all the way and so on. 4 n equal a plus 1, a plus 2, a plus 3, and all the way and so on, respectively. Okay, respectively. And then we gotta use this statement. So we let Q of L be equivalent to P of L plus A minus 1. What does it mean by this? So Pn becomes just L plus A minus 1 because from this equation we have L equal to n minus a plus 1. What happened to just n? N turns out to be L plus a minus 1. Just add both sides by a minus 1 of this equation. So we're gonna have Q, which is equivalent to this statement P, which is L plus a minus 1. Right now, this statement Q Q of L start from 1, 2, 3 and all the way to M. So we're going to use the proof by the first principle of a mathematical induction. So I have to show that P of L is true for any positive integer L, okay, by the principle of, I gotta say just math induction. Okay, great. What can we do next? I'm gonna start with base step. Okay, base step. So what can we do with base step? So we have Q of 1, and Q of 1 is equivalent to, just plug in 1 into L, we gotta have P of A, right? So it turns out to be P of 1 plus A minus 1, which is P of A. What is P of A? P of A is in the first statement, and the first statement is true. What does it mean by this? What does it mean by this? So we gotta have that since statement 1 is true, okay, P of A must be true. Therefore, Q1 is true. That's it, okay? That is the base step. Now let's go to inductive step. What can we do with this? Inductive step, I gotta assume that for any integer k such that k less than m, okay, k is true. Qk is true. And then we have to show that Q of M is true. Okay? We have to show that Q of M is true. Now what can we do with this? We start from Qk being true. So, since Qk is true, what do we have for k less than m? So we gotta have Q1, Q2, Q3, all the way to Qm minus 2 to Qm minus 1. Why? Because k is less than m. So the last one must be m minus 1. And we know that QL is equivalent to P of L plus A minus 1. So we get to have statement P corresponding to these statement Qs. So what do we have? So now these statement Qs are true. Okay. So since I'm going to copy this statement, QL is equivalent to P of L plus A minus 1. What do we have? Okay, we're gonna have that when Q is 1, L is going to be 1, so we're gonna have P of A. So P of A plus 1. Okay, when L is 2, we're gonna have L plus A minus 1, so we're gonna have A plus 1, right? So we have A plus 1, A plus 2, all the way to m minus 2. When L is m minus 2, we're going to have m minus 2 plus a minus 1. We're going to have m plus a minus 3, okay? So we're going to have p of m plus a minus 3. And the last one is p of m plus a minus 2. These statement P's are true. Now, since we assume that the second statement is true, right? So the next statement from P is going to be true. So, since statement number 2 is true, okay, what can we say? So P of m plus a minus 2 plus 1, or this statement P of m plus a minus 1 is true. Okay, this is true. All right. So what do we have? We're gonna have statement Q, which is Q of m, which is true. Okay, so since this statement Q is true, since Q of L is equivalent to P of L plus A minus 1, and Q of M is true. Okay, so we have one more paper. So what can we do next? We've just showed that Q of M is true. So this satisfies the second principle of mathematical induction. So by second principle of math induction, what do we have? Q of L must be true. So it is true for every positive integer L. Okay, and again, since Q of L is equivalent to P of L plus A minus 1, what do we have? Okay, so P of L plus A minus 1 is true for every integer, for every positive integer L. But what is L exactly? L is here, and we know that n equal to L plus A minus 1. So since L plus A minus 1 is n, so L start from 1, right? N is going to be start from A. Then next is going to be A plus 1, A plus 2, A plus 3, and so on, when n is 3, 4, 5 respectively. So n is going to be greater than or equal to A, and P of L plus A minus 1 must be equivalent to P of n. Okay, because this guy right here is n, so we gotta have Pn. So Pn is true. Okay, Pn is true for every positive integer n, such that, what is the condition of n actually? N is greater than or equal to A. Okay, and that's the proof of strong induction, or another version of the second principle of mathematical induction. And that's it for this video. See you in the next video.